some of the services that we're prototyping, or all of them. I will talk about a few, but I think you can imagine some interfaces that use all of this information and context to generate interesting services and allow you to do more things. So another observation that we made, if you think about continuous computing, is to think about what are the capabilities that will be required to service it and provide really, really interesting services that consumers will want. And so the Xbox with Kinect is actually an excellent example of both the hunger for some of these continuous experiences, because you're constantly using gestures to interface with a very responsive system, and the consumer demand for Kinect has been enormous. And also, what are the capabilities that are required to implement it? Now, the Xbox is, in some sense, a fixed function device. It's Xbox plus Kinect, sits in your living room, and we've been focusing on mobile continuous services. But if you look at the Xbox example, what's happened is that you need support all the way up and down the stack to build this integrated experience. You have to have the applications, and you need the languages for developers. You need the right developer tools to leverage all of these gestures. You need specialized hardware, which requires to go down in the microarchitecture and build specialized silicon. And you have to bring that all together into one cohesive whole to deliver a very, very quality experience. And what's happening, and what I think we can all see in the industry, is that hardware companies that traditionally operate here are moving up the stack to try to deliver value. And many software companies traditionally, if you look at Oracle, for example, and Apple, and other examples, are moving farther down the stack than they have in the past. And that's because the co-design required to build these experiences has to be very, very strong, because the load they put on traditional computing organizations is high. Just doing gesture inference, doing continuous transcription of voice, it's a high load, and so you need heavy specialization and really great capabilities. So getting this level of capabilities, especially in low form factor devices, is really challenging. And if we think about the capabilities, they need to be expanded both on the cloud and the client sides. And if we can do that, build much better cloud and client capabilities, we can get to this era of continuous computing and very rich services. So I'd like to give you one example, going back one slide, of some work that my group did fairly recently, which is something we call pocket cloudlets. And we published this in a conference called ASPLOS in 2011. It's scheduled for publication in a few months. And it's just a driving example of the sort of co-design across the client and the cloud that I'm describing. There we go. Nope. Okay, let's go back one slide, please, if you would. We'll do the video in a sec. Thank you. Oh, forward one. There we go. Okay, so if we think about the amount of non-volatile storage that we'll have on devices we wear in our body, it can reach as much as a terabyte in 10 years if you look at the rate of solid-state device scaling. Flash, phase change memory, things like that. And those devices can operate as cloud endpoints. But to do so, you actually need to integrate the architecture of both the device that resides in your pocket and the services in the cloud into one cohesive system. In some sense, they need to be co-designed. And so we came up with an architecture called Pocket Cloudlets that treats the endpoint and the cloud services as a unified system. And one example, and this is what the paper is about, is mobile search. So what we did is we actually built a large cache that takes a fairly large amount of storage by current standards on your device, and we cached a large chunk of the mobile web index. And it turns out that with an architecture like that, where at night you might refresh the index from the cloud, 70% of the time when a mobile user does a search, they find the search result cached on their phone, and you can serve up the search result and serve up the ad in about 4 milliseconds. The alternative is you have to wait for your 3G or 4G link to go to the cloud, go through the process of doing the search, returning the results to you, and that takes on the order of 3 to 4 seconds. So the difference between a pocket cloudlet hit for just doing mobile search and a miss is 3 orders of magnitude. And I can tell you that after I used that service for a while, the friction of missing in the cache and going out and hitting the web index was enormous. I just wanted to go in and out, in and out, in and out, and be looking at all these different things quickly without going, and we think of going, search as being fairly fast. But what it demonstrated to us, the opportunity of lowering the friction and bringing this into sort of sub-perceptual ranges, under 20 milliseconds, created a qualitatively better user experience. And so what I would imagine is as we start to scale up to terabytes on your body devices, you will be bringing enormous amounts of data from the web so that you can have a continuous experience locally without waiting for long transactions to the data center. But those systems need to be co-designed together to make them work well. Okay, so a second example that I'll show is a video from a demo that my group pulled together where we're actually doing rendering in the cloud. So what I'm showing you here is actually on an Android device is augmented reality rendering, and I'll just skip over that to show you the extensions that we made. So we have a mobile, this can be a phone or a tablet, but you're looking on a sheet with some markers. And what the device is doing is it's looking at the sheet through the camera, tracking where it is, and then rendering a pyramid of blocks in the cloud and rendering the shadow on it. Okay, so this is augmented reality or mixed reality. These techniques are actually well known. But what we did as a thought experiment was to say, let's push out some very sophisticated physics processing and graphics rendering into the cloud and see if we can bring all of that information and computational power back through a long loop through the cloud to give the user a very, very rich and robust experience, a continuous experience on a limited mobile device, because the graphics capabilities are just too weak. So now I have 2 people here looking at the same view, and what they're doing is they're shooting blocks at towers. Each device is shooting 1 block, and all of the physics simulation is being done in the cloud and exported to their devices. And so they can have a rich physical interactive experience overlaid on the real world, supported by computation in the cloud. Video, audio, visualization of information. And I think this example gives you a taste of the sort of rich continuous experiences we can start to build once we have this continuous model with rich clients and very strong cloud capabilities. I'm not sure why a Google URL popped up on the screen, but we'll try to prevent that from happening again.
It's a conspiracy.
It always is. Okay, how about slide 9? I think that's a good one. Very good. Thank you very much. So we've talked a lot about the continuous interaction on the client, but I'd also like to talk about the opportunities in the cloud. So what we're seeing in the cloud is a huge explosion of data, and we're generating petabytes of data daily with large scientific experiments like in astronomy, the collider at CERN, and mining the web in terms of literature, consumer information, building business intelligence models, building models of the web for search and rich services. But what's happening is that the cloud is becoming more and more personalized. So in addition to all this big science and digitization of all of these static or slowly growing archives, we're also building large maps of commerce, trends, personalized information, building models about you and your preferences and your tastes, and soon we'll have sensor information streaming up that can be used in mind as well, aggregated with other sensor streams to produce very, very unique insights through heavy and aggressive classification and mining and building of machine learned models. So there are huge opportunities here, both in the scale of data that are being created, as well as the amount of rich services that are now operating, and people are starting to consume more and more of them. So all of this data and all of those services and that constant model generation, hypothesis testing, mining, and then service providing is going to be applied to make a continuous and rich experience for consumers happen. But with all that data, all those data, and the number of consumers growing, and the number of services growing, obviously we need to build very, very efficient clouds to bring this continuous computing model to happen, and to happen broadly and successfully. So Microsoft, as a company, has gone through now 4 generations of data center design, with each generation becoming larger, more integrated, more powerful, more cost efficient, okay, and more carefully designed. And so you can see that the scale of the unit of production has grown, and the specialization of these things has grown to really, really drive the efficiency and reduce the cost of providing these services on a per-service basis. Because as the number of people using these services grows, and the amount of data driving those services grows, and the number of services that people require grows, that puts huge pressures on cost and the amount of machines you need to power in the cloud to make all of this happen. And I'm delighted to say that we have wonderful relationships with hardware partners and systems partners, many here in Taiwan, helping to design the next generation machines and data center units to continue scaling out in terms of efficiency. But in the cloud, it's 2 things. It's both the scale of the data centers, these modular data centers, and the efficiency that both need to be driven. We need to drive the scale up, and to keep the costs under control, we need to drive the efficiency up continuously. And without improving efficiency, both energy efficiency, materials efficiency, and cost efficiency, it won't simply be possible from a cost perspective to grow these services out. As another example, in terms of the sensitivity of much of this data, genome sequencing has moved forward enormously fast. And in 2004, sequencing a genome cost about $3 billion. This was a grand challenge. There were teams of scientists. New algorithms had to be developed. And then with the techniques becoming widespread and the cost of computing dropping, today we're able to sequence a human genome for about $45,000, which is about 60,000 times more efficient than it was previously. And then going forward, the projections are that it may cost as little as $500,000 to $10,000 per genome within just a few years, and then a few years after that, $100 per genome. So now you can start thinking about sequencing everyone's DNA, or most people's DNA, for a very small amount of money, provided that the economies of scale and the efficiencies of all of that heavy processing in the cloud continue to improve, and that the amount of storage we can hold in the cloud continues to grow. But when you think about having your DNA sequenced, the most personal thing, the blueprint for you, it is incredibly sensitive. And your DNA can be processed and analyzed and mined to predict all sorts of things, many of which right now we don't even know. Your personality, your behavior, your patterns, your preferences, many of those are likely either encoded or have signals in your genome that may encode them. So there's incredibly rich information here and incredible opportunity, but also danger, because this is incredibly sensitive.